This is an experiment on measurement of the friction factor in pipe flow. And as we know, flow in pipes is very important in a variety of applications, particularly power plants where you have miles and miles of pipes. And what happens is that you have friction on the walls of the pipes that will reduce the effective pressure as we go down the pipe. For example, if you just go to Alaska, the Alaskan pipelines, you have to invest a lot of pumping power to transmit the fluid that is pumped from the soil. As time goes on, the pipe from the inside fouls up, and then you have roughness, and the roughness will increase the pressure drop. And I explain in my lecture the concepts behind it. So for this experiment, what you're going to do is measure the friction factor in a variety of configurations. 4 different pipes will be measured, and each one has a particular diameter and particular characteristics. 3 out of the 4 will be smooth pipes, and the 4th one will have calibrated roughness so that we can mimic and simulate the fouling that takes place in large diameter pipes in pipelines. So I'm going to go through an explanation of the setup and how you do your measurements, and then we'll turn on the system because it's a little bit noisy. After we just kind of get through the explanations, we'll turn it on and go step by step. So what you see here is a test stand. This is a huge test stand with a frame, so it's kind of movable. And on this test stand, we have 4 different pipes increasing in diameter. So the test section of each pipe is in the center from here to here. So that's the test section. So we have a small pipe that has an inside diameter of 8.15 millimeters. As you can see here, this is a copper pipe. And it is instrumented with 2 pressure taps. So you can measure the pressure at this point and the pressure at this point. And we're interested in measuring the pressure drop in this section. In addition to this, it's also instrumented to measure the temperature. So you have a thermocouple that also measures the temperature of the water as it's flowing through. Moving on, we have a second pipe that is slightly bigger. The diameter is 11.8 millimeter with a longer test section for the pressure. So the length here is 1.143 meters. The length of this is 0.78 meters. So this is longer length and larger diameter. And then finally, out of the set of 3 for smooth sections, the 3rd pipe has a diameter of 17.5 millimeter and a test section length of 1.98 meters. So we're going to measure the friction factor in these 3, assuming that the inside is very smooth. So we have correlations to determine the friction factor for smooth pipes. Once we finish that, then we have a 4th pipe, and this pipe, it has a square cross section, as you can see here, and it has a short test section, and therefore the length here is 0.337 meters, so from here to here. And inside this pipe, there is a rough surface that is already machined to mimic the fouling that takes place in actual operating conditions in power plants. So the inside, if you look at it, it has a ribbed structure, and the ribbed structure, if you can zoom in, the ribs look like what you see here. So these ribs, they have a cross section. If you take a cross section of those, then you see in the cross section, it looks like this. So you have a pitch between one rib and the other, and also a thickness. So you have here, this is 0.3 millimeter wide, and the height of this protrusion is 0.3 millimeter. And then the distance between, or the pitch, is 3.08 millimeter. So with this type structure, we have a correlation from which we can determine the effective sand grain roughness for that particular pipe and do our measurements as well. So this is all in parallel, and the flow is a closed circuit. So if you can see that generally the flow here, we have a fluid flow, we have a return tank, it's water driven system, and you got a main pipe for the flow, and then it distributes the flow in parallel. In our measurements, we're going to shut off all of the valves except for one where we do the measurements. So for example, if you look on that end of the test stand, you'll see that we have 4 valves, and the 4 valves control the flow portion that goes into each one of them. If you shut off, for example, these 3 valves, this one, and this one, and this one, and you open the top one, then you have already determined that no flow goes into the bottom 3, and the full flow will go to the top one. And if you open it completely, that will give you 100% of the flow rate that is attained with the centrifugal pump. So that's on the controls at the top here. Now if we look at the controls on the bottom, the system is driven by a centrifugal pump, and you can see it here, in which we have, this is a Dayton type centrifugal pump, and then it's not what you normally have in, say, pools or jacuzzis to push the flow. And the flow now goes through this flexible pipe. So this is the first thing it encounters. And as it goes through the flexible pipe, then we have attached a turbine type flow meter. And the turbine type flow meter is right here. And the turbine type flow meter, it has vanes, and the vanes would rotate, and the speed of rotation is proportional to the flow rate. And every time you have one rotation, it introduces an electromagnetic field that is coupled by induction to the sensor on the top, and that sensor gives you a pulse of corresponding to rotation. And this pulse is going to be displayed when we turn on the system on the top here. Then you'll see the number of pulses per second, or the turbine flow meter output in hertz. And the basic idea behind measurements is that this flow meter, the frequency that you see is proportional to the flow rate, and the proportionality factor is given here as K equals 2690 pulses per gallon. So if you just have so many 2,690 pulses, then you know that you have a gallon. And since the pulses are measured per second, then this will be per second, and then you'll be able to immediately determine the flow rate. The selection process for each one of these flow meters, or for each one of these pipes, is by a hydraulic valve. And the hydraulic valve, we have a left and a right, and each one has an arrow. For example, if I'm selecting pipe number 1, then I have to move this to the left first, number 1, and then if this was here, then the right will turn to number 1, and now I'm secure and selected number 1. If I want to now switch to number 2, then you turn the left, and then you turn the right, and you're on pipe number 2. Very simple process here. So let's select pipe number 1 already here. And now we're ready to go, and we're going to turn on the pipe and show you the experiment. Before I do that, while it's a little bit less noisy, I'll show you the data acquisition system. So the temperature sensors, as you can see here, there's the wires going through, all of the temperature sensors, and the pressure tap sensors are going into a data acquisition module. When you work in the industry, that might be your job, end up actually designing this unit here. So it's a little bit beyond the range of topics that we cover, but you will be probably designing that unit and connecting it. However, once this is designed and connected, as you can see here, then you will connect it to a data acquisition system, which is a lab view, a standard one that we use on this computer. So if you just look at it here, you will see that you have a lab view is a program that we use in several experiments, and you have an icon showing the pipe flow. You click on this icon, it shows you lab view 8.2, and it gives you a display screen that has diagnostics, and it has data acquisition analysis. So the diagnostics are for the design process and that you're not going to be concerned with, but you're going to be doing your data acquisition analysis here. And you will see that you have 4 panels on the top that are designed for pipe 1, 2, 3, 4, giving you the temperatures in degrees centigrade as a function of time. This is a running average. The sampling rate is 5 hertz for this experiment, which is reasonable. And we use a 10-point running average to smooth the data within the data acquisition system. And in the bottom here, you have a turbine flow meter, and you will see the pressure that is measured in Pascal here, so thousands of pascals. This is 75,000, for example. You'll see a panel here that shows the turbine, flow meter. This is the calibration number that converts the number of pulses to gallons per minute, and that we will take that number from the measurement that we'll do on the test stand. So we'll put it in here and press enter, and that will perform the calibration and give us the flow rate. We can select the pipe on the software by moving this, grabbing the red dot and moving it to the appropriate pipe. As you can see, very fancy here. This is done by Ben, but you could, in the future, you probably will do something like that. In addition, there is also display with the friction factor that's computed from the correlation with the as a function of the Reynolds number, so you can see the range of friction factors that are possible. But you're not going to use this. You're going to use your own correlations and analysis as I covered in my class presentation. So now we're ready to go. So we're going to go back, turn on the system, and perform a measurement right from the beginning so you can see what's happening. First of all, I make sure that all of these valves are closed. They're already closed. And this valve is open to full flow. So I'm going to just keep going until I cannot go anymore. So it's full flow. And then you're going to turn on the pump. And you turn on the pump by pushing the start button at the bottom here. So it's noisy already. So now we have full flow for pipe number 1 right here. It takes maybe a minute or two to go through. So the flow is being established. Now I'm ready to do some measurements. The only thing that I would like to measure now is the turbine flow meter output in hertz. And that is shown here. So at this moment, we have a flow rate corresponding to 313 hertz. And that is the number that we will use to do our calculations and also to input into the software. So we'll let this go on for maybe 2 minutes to be established. And the process, we're ready to do our measurements and data processing. So we would go to the software, to the data LabVIEW software, and right here on the turbine flow meter, we have to put in 313 and push enter. So it is acquiring data, but in order for us to see the data, we have to push play or the run button. So and press this to record. So now we have a recording process going on. You see the results of calculations for the friction factor as a function of the Reynolds number. You'll see the temperatures of the 4 streams, although 3 of them are not running, but still recording temperatures. And right here, you will see a little blip indicating the pressure drop. Right here is 50,000, 75,000. So it is approximately 65,000 PSI. or 65 kilo psi. Actually, it is right here, 64,700 Pascal. And that is basically the type of measurement that I need. And then once I do the measurement, then I press stop, and this will stop the recording, so you have all of the data. And then after you stop, let me stop it again here. After you stop the data, then we will be ready to save the data and then move on to a different pipe. And well, actually, before we move on to the different pipe, for this particular one, you have to, this is the maximum flow rate, and you have to decrease the flow rate in 10 steps to the minimum. For example, if you're going to look at the turbine flow meter output, as I close the valve to reduce the flow area, what will happen is that the turbine flow meter output in hertz is going to change. So right now, it's still at 312 and 310, 308. So you can see now there is a decrease in the turbine flow meter output, and that is what you need to do to go in 10 steps. And with that, I think we're finished with the experiment, and you will be able to switch from one pipe to another and perform all of the 10 sets on each one. And we'll see you on another experiment.